G'day viewers. In this segment we'll talk about the Border Gateway Protocol, which is used to find routes across the internet. So we talked before about the fact that the internet is comprised of multiple independently run parties, such as ISPs, and we need to find routes across those parties that respect the policy constraints of the different parties. What we haven't told you so far is how those routes are actually found. Well, in the internet, it's with a protocol called BGP. In this segment, I'm going to give you a brief introduction to some of the issues that we find in BGP, rather than extensive coverage, because BGP is kind of complicated, and you might go over more details in an advanced networking course. Okay, so just as context, recall that we're viewing the internet as made up of all of these different independently run networks. We have here content distribution networks, ISPs, and just generic networks here. And we might be trying to find paths through this network from a source here, say, prefix C1, acting as a source address. That's going to send along some path through the internet to get to a destination here, such as A1. Now, which path will be chosen through this graph? Well, I've just picked an arbitrary path there, but the routing protocol needs to decide which one will actually be used. And that's exactly what BGP does. So here's just an overview of some of the aspects of BGP, and then we'll move into some examples. So BGP computes interdomain routes, as they're called. These are routes across different entities, such as across ISPs in the internet, as distinct from intra-domain routes. Intra-domain routes are routes within one single network, such as within an ISP. Now, we've already talked about distance vector and link state protocol methods for computing routes. BGP, it turns out, is what's called a path vector protocol. It's closely related to a distance vector protocol, but a little more general. In a path vector protocol, what happens is that route announcements, which carry the path from the point in the network back towards a destination, are propagated throughout the internet. So you can see here the blue line is meant to represent a route announcement, which is propagating out in the network. It's propagating out from prefix F1, so it's going to tell people how to get to F1. And if we look at it inside ISPA, we might receive a route announcement that says something like, well, to get to prefix F1, that's the destination here, here is a path you can use. It goes ISPB netf. Well, they are the networks through which you go along this path once you leave your ISPA to get to the destination. And the way you access this path, the next hop is to go via the IXP. That's here. So you just send across the link to the IXP and you'll be on your way along this path. That's an example of a path vector announcement. Okay, a little more terminology about BGP before we see examples. First of all, we're used to talking about ISPs here as the different parties in the internet, but in BGP terminology, these are ASs. That stands for autonomous system. All sorts of networks might be autonomous systems. You don't have to be an ISP. It could be a content distribution network, a campus network, and so forth. So ISP and AS are not one-to-one. We're also interested here in what are called the border routers. These are, not surprisingly, the routers which are on the border of the ISP, and they send routing announcements to border routers that are on the edge of another ISP or another AS to which this AS is connected. So we're really interested in the announcements that flow between the ISPs here. There are also announcements that can flow within a network such as an ISP, but I'm not looking at them here. We're really going to focus on these route announcements as they move around. And I'll tell you that a route announcement, just like we saw in that picture before, contains several things. It contains an IP prefix, that's the destination that you're trying to reach. So that was F1 in our example on the previous slide. A path vector that you go through to reach this destination. I forget what that was maybe ISPB and netf on the other side. And a next hop that you use to get onto this path, and that was via the IXP or Internet Exchange Point in our example. Now, the reason that you actually carry the list of ASs, the whole path, rather than the distance, actually if you think and just compare to a distance vector protocol, in a distance vector protocol, you'd be sending a prefix or a destination, a next hop, which way to go maybe, and a distance metric to decide which way is best. In BGP, we don't send this distance metric, we just send the whole path as a list of ASs. One reason this is done is that the designers were very worried about loops between multiple ISPs. Just imagine that packet zapping around across multiple ISPs. That would be pretty nasty. And so the idea is that if you list the whole path, you'll be able to recognize directly if there's a loop, if you've already gone through a particular ISP, and you'll be able to not use that route. And you're going to see two kinds of flows in network diagrams. I'm primarily going to be talking about the route announcements, how they go out from a destination to other places in the network to tell you how to reach that destination. But if you think about actual traffic that is forwarded along the internet, realize that this traffic will go in the opposite direction to the route announcement. So it will go from wherever you are in the internet towards that destination. Well, here's a little example just to look at to see how some simple announcements would propagate. In this diagram here we have three ASs. You could think of them as ISPs if you like. AS1, AS2 and AS3. I'm just going to look at the announcements that propagate out from prefix C. So that's the destination. Well, along these dotted paths you can see that announcements, BGP announcements carrying path vectors propagate out in the network. And I've shown them here above. Now, this announcement here, to reach prefix C, you go via AS3, and the next hop is here, R3A, is the announcement you would see if you would look over this wire, connecting this border router in AS3, R3A, to a corresponding border router in AS2, R2C. As that announcement propagates further along, if we look at it over this link here, between AS1 and AS2, you can see that now the path has changed. So the path you go through now is AS2 and AS3 to get to C, and also the next hop has changed. Now to access it you go via here. And this last announcement just looks at what you would see actually in the middle here of AS1, since it can't really propagate any further out to A. Similarly, you'll note that routes towards prefix C are also propagated along this other path along the bottom of the diagram. So it's not the case that each AS is making a single decision for routes towards each prefix. In different places in the AS, different routes are propagating using different next hops and so forth. So we can see as we go down here, I'll just circle the corresponding places where these announcements are, that here we go out, the paths actually look the same in terms of the path vectors, the ASs that you go through, but the next hops are all different. Here, actually let's do this one here. You can see that AS1, which here's this announcement, goes via R2B, not R2A, to get to C. So anyone down in the lower portion here of AS1 is probably going to go via a path here to reach C, whereas anyone up here is probably going to end up going via a different path to reach C, even though they'll go through the same sequence of ASs. I've also drawn darker arrows on this diagram, and those dark lines represent the flow of traffic, which is the opposite of the flow of the routing announcements. So for instance, over the top of the diagram, a dark line goes from C all the way through the top of the diagram to A, going in the reverse direction that the route announcements propagate. Right, well, so you've now seen a lot of the mechanics of BGP. I haven't explicitly talked about policy though, and that's really what we wanted to get out of this. So far I've just shown you a path vector. How do we get this policy of our ISPs being able to make decisions which suit their need, choose routes which suit their need? Well, in two ways. When a border router, the first way is that when a border router announces paths to the border routers of other ASs, it only announces paths that it's willing to have those ASs use. It doesn't need to announce other paths that might exist, but it doesn't want someone else to use. It can just withhold them and filter them out. That is applying policy. A second way is that when a border router in an AS hears multiple routes towards a particular destination prefix, it can choose whichever one of those routes it would like to use. If this was a distance vector protocol, we choose the one which has the shortest distance. In BGP, we don't have to choose the one that has the shortest path. We can choose whichever one we want for our own reasons, which may have to do with strange contractual requirements between the companies, for instance, which you wouldn't normally think would be part of a protocol. But BGP can accommodate them by letting you choose the particular route you want, regardless of the length of the path vector. So BGP is looking a little tricky. Let's see an example, and then we'll call it quits, and you'll have a rough idea of how BGP works. Here's another diagram. In this diagram, I have 4 ASs. And I'm going to focus on this one here. This is AS2. We'll look at the route announcements it makes and receives and how it chooses its own paths to get elsewhere in the network. I will also tell you that in terms of commercial relationships between these ISPs, two things are going on. AS1 is buying AS2, the one we're looking at, is buying transit service from AS1. AS1 up the top here is this big ISP that's kind of providing transit service to everyone. It will connect everyone to one another if you pay it money. AS2 is also getting a peer service with AS3, and it looks like they're doing that to exchange traffic between A and B. Just for their traffic between A and B. That's what you would do with a peer service. So we want to see how paths are found which are consistent with these policies. What happens? Well, several kinds of route announcements flow around. First of all, we're going to look at what are called customer route announcements. The customer side is really the flip side of transit. For an AS like AS1 to provide transit service to let everyone reach a certain prefix and to allow traffic from that prefix to go everywhere else, the prefix needs to get to the transit provider. That destination needs to tell the transit provider who they are, that they want service. This is a customer announcement. You see it's going up here. It's labeled CU in this diagram. So AS2 is going to tell AS1, okay, here's an announcement to prefix A, that's the destination. The path is going to be AS2, just via me, and it's going to send that to AS1. That's the only customer announcement. This is pretty straightforward, really. This is really just saying to AS1, hey, prefix A exists down in me, AS2. Well, let's look at the flip side. AS2, the one we're looking at, that's this one here, is also going to receive transit routing announcements from AS1, which will tell it how to reach other prefixes in the internet. What transit announcements will it receive? Well, AS3 has B as a prefix destination and AS4 has C as a prefix destination. Both of those are going to advertise B and C to AS1. And since AS1 is providing transit, it will tell AS2 about the possibility of reaching these destinations. So AS1 will tell AS2 a couple of routes. For B as a destination, AS1 will say, hey, there's this prefix B. You can reach it via the route AS1, AS3. You can see our path has now gotten longer. So we're now going through two ASs to reach that destination. I'm ignoring the next tab here. And similarly, AS2 will hear from AS1 that it can reach prefix C via the path AS1, AS4. Okay, that's a transit announcement. But wait, there's more. AS2 here is also going to receive a peer routing announcement across here. And it's also going to send a peer routing announcement. So what are they for? Well, this is really, AS2 wants to tell AS3 that it is allowed to send to A over this link, and AS3 is also going to tell AS2 that it can send to B over the same link. So AS2 is going to say, well, AS3, you can send to A via the path AS2 over this link, and AS3 will say, hey, AS2, you can send to B, and the path is AS3 over this link. So now we have all of these different announcements that have been received by AS2. So what route will AS2 actually choose to use in the internet? Well, let's do an easy one first. AS2 will actually only hear one route to C. So the way from AS2 that you're going to reach C is actually, this is the way the traffic will flow. It's the dark line. And the routing announcement that we're selecting to follow that is the one that propagated in the opposite direction. That's the only one we heard, so that's what you're going to use to reach C. What about to reach B? Well, we actually heard two announcements. We heard one which came up here, the transit one, and we heard one which came here from AS3 directly to AS2. Since AS2 has now heard two announcements, it can use its policy to decide which of them is better. And the answer is that the peering service is better because peering service is typically free, whereas you're paying for transit service by the volume. So AS2 is going to send over this link to reach B. And similarly, you can work through on your own what's going to happen for the route that AS3 and AS4 will choose to be able to send from B to other destinations on the internet. Well, that's our simple example of BGP. So you've now seen a little bit about how it works, and hopefully that gives you a feel for it. There's actually a lot more here to BGP than the basics and all sorts of strange effects. We're going to leave that though for a more advanced networking course. I hope that one thing I would like you to take away from this is an appreciation that the policies which ISPs use, is a substantial factor in the routes which are used in practice. AS2 could have chosen any of two paths, and they're really quite different, and different things would have happened, and it totally depended on what AS2 wanted. In fact, there are various issues like, can you even be sure if everyone chooses paths independently that the overall routes will actually work? This is an interesting problem, something that researchers look at, how we guarantee that will be the case. And there are other key factors that you might care about for BGP. We're not going to look at them now, but I'll just mention some of them so you know what are interesting areas to find out more about if you would like to. One is convergence, just how fast these protocols converge when anything changes to find a new route. Another is scalability. BGP needs to scale to the size of the whole internet. So we sort of want to know how many routing messages are going around and how much work routers have to do. And also you'll note that I skipped the integration between the BGP we looked at, where messages are sent across ISPs, with the routing that goes on inside ISPs. Really those two parts of routing need to be integrated together well for overall internet routes to work well. So that's it for BGP. I hope you've learned a little bit, and we're done.